Good afternoon, everyone, and welcome to this webinar. My name is Wolf Bracke. I work at Ghent University in Belgium, and I'll discuss the durability and measurement uncertainty of airtightness in extremely airtight dwellings. I'll present the results of research conducted in 2013 together with Professor Laverge, Van den Bosse, and Janssens. After a short literature introduction, I'll first discuss the repeatability of airtightness test results, as well as seasonal variation, so we can differentiate between normal or expected variation in results and durability problems, which is discussed afterwards. Most of you will be aware of the importance of airtightness as you are watching this webinar. More and more airtightness tests are performed, and the results can have financial consequences in the form of fines and subsidies. So this stresses the importance of reliable test results and also raises questions about the long-term performance of airtightness, which is why we conducted this research. In literature, we found a study by Delmotte and Laverge, which Valerie already mentioned, testing the measurement uncertainty under both repeatability and reproducibility conditions. For the first case, 10 tests were performed on the same building by the same operator using the same test equipment. For the reproducibility conditions, the same building was tested 10 times by different operators, bringing their own equipment, also on different test days. So in the first case, we see a standard deviation of 2% and a maximum variation of 4%. These numbers rise to 3 and 8% under reproducibility conditions as a result of the impact of building preparation, building equipment, and weather conditions. Something about seasonal variation, which is also discussed by Valerie already. Kim and Shaw have performed research about seasonal variation of airtightness in a wood frame construction in Canada. We can see a clear yearly fluctuation in the chart and a maximum variation of about 18% during the year, which is explained by the authors by the swelling and shrinkage of wood as a result of seasonal changes in air humidity and temperature. They tested actually 2 buildings, one more airtight and one less airtight, and the effect was visible in both buildings. We also looked at durability studies, but at the time there were not so many available, and the ones which were available was very hard to draw conclusions, because in most part of the tested houses, some refurbishment had already been taken place, or different operators performed the tests, or the test conditions were different, which makes it hard to draw clear conclusions. So now we go on to our own research. First, we'll discuss the repeatability of the measurements and seasonal variation. For this part, we found 2 test objects, 2 passive show houses in Belgium. On the left hand, we have a masonry construction. On the right hand side, we have a wood frame construction, because there was already some discussion about seasonal changes in wood frame. We wanted to compare both construction methods. So both are passive houses, so they have a very good airtightness level at the end of the construction. First of all, one of the most important things we noticed was the influence of building preparation. There exist European normative documents which explain how to prepare buildings for a blower door test, but these documents still leave room for interpretation. Sometimes local guidance documents offer suggestions. In Belgium, that's the case. So one of the important things we noticed was the locking of external doors. Nothing is mentioned in the normative documents. The Belgian guidance documents suggest you lock the door by key, and we found that it actually has a very large influence, especially in these large door frames. The corners can be bent a little, or the door is a bit distorted after some time. But if you close the door with a 3-point lock, the corners are closed much better, closing the rubber gaskets and limiting the air leakage around it. Another important point was the disconnecting of the ventilation system. This can happen at room level, at the local ventilation vents, or this could happen at the central supply and exhaust, as we see in the middle picture on this slide. There are roof penetrations which can be centrally closed. So of course, if you seal the ventilation system at the room level, you will include all leakage through the ventilation system and the ventilation ductwork, while in the second case, this is excluded from the measurements. The position of the blower door is also an important point. Belgium guidance documents suggest you install the blower door in the most airtight window opening or door opening. But of course, you cannot know which is the most airtight without performing multiple tests. And as we found there are sometimes large air leakages around the doors, it can have large impact. One thing which is suggested in the norm or is obliged is to close water locks, fill water locks. But there's something which is easily overlooked, was shown to have a relatively large impact on the measurement results. This chart shows the impact in cubic meters per hour at 50 Pascal pressure difference. So apparently these small differences in building preparation can have a large impact on airflow, and especially in these very airtight buildings, it has a very large relative impact. So as mentioned on the slide, a difference of 50 cubic meters per hour represents 20 or 35% change for the two test subjects. Here we see the results for the masonry construction. So we had 10 test days during a 15-month time span. The repeatability is in line with literature. We see some variation during the year. So we asked ourselves, is this a seasonal change we're noticing? But actually in summer they are higher air leakages compared to the winter measurements. So this is contradictory to the literature. One possible thesis could be that a different thermal dilatation of the masonry construction and the plasterwork ensuring the airtightness leads to larger cracks in summers at corners or joints. But this is only a thesis. We're not sure. It should be checked in laboratory conditions maybe. But a more straightforward explanation for the differences is that these differences are more random and a result of the changes of the ductwork connections, which are dismantled a lot during the tests. So you see the small picture on the left of the slide. The roof penetration for the ventilation supply and exhausts are not sealed with the correct method. So there is no rubber gasket used, but they used pieces of tape. And it's very easy to get an additional small leakage or if you change it a little bit, you can tape it back. So this leads to differences in air leakage around the penetrations. For the second house, we see a very constant measurement results during the first 6 measurement days. Afterwards, we see a large drop of 40 cubic meters per hour. There were some months during the first 6 and the last 3 measurements. The last 3 measurements were more a follow-up of the research. And we noticed that there was a completely different result, but we have no idea why. We asked the owner of the show house. They did not have an explanation. They were just happy that the airtightness seemed to have improved over time, but I cannot believe this is really the case. So something has changed. Maybe there's a problem with the measurement calibration or the measurement equipment calibration. We're not sure about that. So now we go on to the durability of airtightness. For this part of the research, we found 15 owners in 2 passive house neighborhoods who agreed to let us perform new tests and compare the results to the original certification tests. At the moment of testing, there was 3 to 27 months between the original test and our tests. So these are all masonry constructions from the same firm as the show house from the previous part of the research. They use the same building methods. We found an average increase in air leakage of about 32%. Of course, there's a relative increase. These are very airtight houses at the first measurement, so the absolute difference of airflow is limited. Important to notice maybe is that according to our tests, most of the houses do not reach the passive house limit of 0.60 air changes per hour at 50 Pascal. We can also use this chart to study the workmanship reproducibility. All houses are built by the same contractor using the same building materials and airtightness products. The layout of the building is virtually identical, so that's a nice case. We cannot see that there are large outliers. Maybe there were outliers above 0.60 where the firm building the houses had done some corrections to get below the passive house level. That's possible. We don't know about that. We see no significant correlation between the age between the measurements and the relative increase in air tightness or air leakage. So we can maybe conclude there is no gradual deterioration, but that the increase in air leakage is rather the result of individual local problems which were observed during the test. So as I mentioned before, from the study from the show houses, there are a lot of air leakages around doors and surface penetrations, especially ventilation ductwork through the roof, which is possibly responsible for this increase. But of course, we cannot study these numbers without excluding the effect of reproducibility. As I mentioned before, how the building is prepared is very important for the result. So to conclude, we did a study on very airtight houses. The measurement uncertainty is in line with literature, but for a better reproducibility, maybe more specific building preparation guidelines are needed. We do not observe clear evidence of seasonal variation. And in the long term, most houses show the larger leakage over time, but this is still small in relative values, and it's hard to exclude the impact of building preparation. So thank you for your attention. If there are questions, I'll try to answer them. You can also contact me later on, or if you're interested, you can find a paper online with the same title as this presentation. Thank you.